Hi everybody. So let's push on in our discussion of equivalence relations, and now we're going to kind of come to the key point I think about them, which is that they are a way to divide a set up into pieces. And those pieces are called partitions, and the collection of pieces is called a partition of a set. And so we're going to make that we'll give a precise definition for that and see what the relationship is between that and equivalence relations on a set. So, oh dear. There, you got a little glimpse behind the window of all my stuff here. Okay, so here's the crucial definition, and this is a definition you should definitely know. A partition of a set is a set of non-empty subsets of the set whose union is the full set, and whose intersection of any two of them is empty. So intuitively, a partition is a division of A into disjoint subsets. If you were going to draw a Venn diagram of a partition, here would be your set A. This is A. And you would have subsets I guess maybe this isn't really a Venn diagram, but here would be sort of P1, P2, P3, P4, and P5. So this would be a partition of A into 5 subsets. Pi intersect Pj is empty if I is not equal to j. And the union, as I goes from 1 to 5, of Pi is A. And so there are no points that lie on these dividing lines. All the points of the sets lie inside one of these partitions. So there's my picture. So you can see where the word partition comes from. It's a good name. It's a way to chop up a set into disjoint pieces. Okay. So we've seen some examples of these. I mean, we've over and over again used the fact that integers can be partitioned into even and odd integers. So the two sets here, the even and odd, the fact is that every integer is either even or odd. So it's the evens union the odds. But no integer is both even and odd. So the even intersect odd is the empty set. And that makes it a partition. We also, this is sort of a related one, but using 3, the congruence class is modulo 3. Remember, those are the arithmetic progressions. So the 3 congruence classes are 0, which are the multiples of 3, positive and negative. The things which are one more than a multiple of 3. And the things which are 2 more than a multiple of 3. So this is the collection of 3k, k and z. This is the collection 1 plus 3k, k and z. And this is the collection 2 plus 3k, k and z. And how do we know these form a partition? Well, we know these form a partition because of the division algorithm. Remember that the division algorithm says that every integer A can be written A equals 3q plus r, where r is 0, 1, or 2, and this is unique. So in other words, when you take an integer and you divide it by 3, you get a remainder of 0, 1, or 2. And here what we've done is we've basically divided up the integers into 3 classes, depending on what the remainder is when you divide them by 3. The ones which have a remainder of 0, the one which have a remainder of 1, and the ones which have a remainder of 2. And we can write them in this way, or we can also write them as the equivalence classes using the notation from the last video, last section. The equivalence classes, this is x is congruent to 0 mod 3, x is congruent to 1 mod 3, and x is congruent to 2 mod 3. And then just to give a couple of non-numerical examples, we talked about the books with one author, and the equivalence relation was that they had the same author. Well, the equivalence classes then are all the books by a given author. And the partition is you take the collection of books and you divide them up by their, at least books with one author, and you divide them up into classes based on who the author is. So you would have the Herman Melville class and the J.R.R. Tolkien class and the, Donald Trump class. And each of those would be an element. And then since every book with one author has an author, every book would be in one of those classes. And then lastly, you could group people by the county, and let's say just people in Connecticut by their county of residence. If everybody has one county of residence, the partition is you take the group of people who live in Connecticut and they're divided up by county. And you can only live in one county, so the people that live in one county and the people that live in another county are disjoint sets. And everybody lives in some county. So the union of the counties is all the people in Connecticut. So these are examples of partitions. And we have this relationship between partitions and equivalence relations, and it's important enough to be called a theorem. We don't have that many theorems. We tend to have propositions, but theorems are the things that are really important. And what this theorem says is that if you have a set and you have an equivalence relation on it, then the equivalence classes form a partition of the set. And in fact, it's if and only if. Namely, if you can also go the other direction. If you have a partition, you can get an equivalence relation, but that's going to be a homework problem. So let's try to prove this theorem. And it's always a good idea to think about what we have to show. We have to show two things. First of all, that the union over all A of the equivalence relations, of the equivalence classes, is the set A. And second of all, we have to show that if two equivalence classes are different, then their intersection is the empty set. Now, this may seem a little bit strange, but what's going on here is that these equivalence classes, I mean, if A and B were equivalent, then the equivalence class of A would be equal to the equivalence class of B. And so they would correspond to the same element of the partition. The condition is that different elements of the partition have empty intersection. So we have to make sure that the equivalence class of A and the equivalence class of B actually correspond to different elements of the partition, and then we have to check that their intersection is empty. The first one is clear. To prove that they're equal, we have to show that, to prove these two sets are equal, we have to show that they're subsets of one another. Since A is a subset of A for all A and A, the union over all A in A of A is a subset of A, because if you belong to this union, that means you belong to at least one, possibly more of these collections of equivalence classes, but they're all contained in A. So the union is contained in A. The more interesting thing is this disjointness. And that will prove by the contrapositive. Let's suppose that we have two equivalence classes that have non-empty intersection. So that means there exists an x that belongs to A and B, right? And that means x is equivalent to A, x is related to A, and x is related to B. So by symmetry, remember this is an equivalence relation, and now you're going to see why we need to use, oh, you know what, I cheated here a little bit. I used a property that I didn't mention, which is that A belongs to the equivalence class of A. And why is that true? Because this is a reflexive relation. So I have to use the properties of an equivalence relation. And the place I use reflexivity is in the fact that the equivalence class of A contains A. And so I proved that this is a subset. But I didn't prove equality. To prove that they're equal, I take an A in A, and then the equivalence class of that A is contained in the union of all A. And therefore, A is contained in the union. My apologies, I skipped a step. So we used reflexivity up here. Now we're going to use symmetry and transitivity. By symmetry, we have therefore that since x's are A, we have by symmetry A is related to x. And now we have A are x and x are b, so we must have A are b. In other words, A and B are actually equivalent. Now, if that's the case, then the set A, which is the collection of x such that x is equivalent to A, is actually equal to the set B, which is equal to the set of x such that x is equivalent to B. And why is that true? Well, first of all, if x is in, remember we have to prove that they're subsets of each other. If x is in A, then x is equivalent to A, and A is equivalent to B, so x is equivalent to B, so x is in B, in the equivalence class of B. And if x is in the equivalence class of B, then x is related to B, and A is related to B, so B is related to A, and then by transitivity, so x is related to A, so x is in A. Whoops. In other words, if these two subsets, these two equivalence classes have an element in common, then they're actually equal. And so if they're, that's so what we've shown is that if A intersect B is not empty, then A equals B, and therefore, if A is not equal to B, then their intersection is empty. And that's what it takes to be a partition. The equivalence classes cover the set A, and the different elements of the partition don't meet each other. They're disjoint. So every equivalence relation gives rise to a partition of a set into equivalence classes. And as I mentioned, the converse to this is also true. Namely, suppose you have a partition. So here's your set A, and it's divided up into these sets corresponding to the partition, P1, P2, P3, P4, and P5. And now you can define an equivalence relation. Well, you can define a relation by saying x is related to y if x and y belong to the same element of the partition, the same subset. And it turns out that's an equivalence relation, and that's going to be a homework problem. So you have to check that condition implies that the relation is reflexive, symmetric, and transitive. So the upshot of all of this is that if you want to take a set and divide it up into disjoint subsets that cover the whole set, what you're really doing is constructing an equivalence relation on the set.